We have seen that when W is a vector space and A is any set, the space of all functions from A into W is a vector space in the same way the real-valued ones are. Addition is pointwise, and so is multiplication by scalars, for exactly the same reasons. But there is no reason to use the same W at every index. Given a collection of vector spaces indexed by I, their Cartesian product is defined as all functions with domain I whose value at each I lies in the ith space. The book gives a concrete example. On the unit sphere, the tangent plane at each point, translated to the origin, is a subspace. An element of the product of all of those assigns to each point of the sphere a vector parallel to the tangent plane there, a vector field. The jth coordinate projection on a product space is still evaluation at j. Here its values lie in a vector space rather than in the reals, so it is called a coordinate projection rather than a coordinate functional. The key point is that the vector operations on a product space are uniquely determined by requiring that all the coordinate projections be linear. The sum of two elements must be the one whose value at each j is the sum of their values there, and likewise for scalars. So the theorem, the Cartesian product of a collection of vector spaces, can be made into a vector space in exactly one way so that the coordinate projections are all linear. The proof is the earlier axiom check verbatim, which never asked that the values lie in one space. Now when the domain is itself a vector space, we single out from the function space the subset consisting of all the linear mappings, and that subset is written of V and W. The first theorem is a formality. Is a subspace of the space of all mappings. The sum of two linear maps is linear, so is a scalar multiple, and the zero transformation is in there, so it is non-empty. Next, composition. The composition of two linear maps is linear. The statement is elementary, but it needs the obvious hypotheses on domains and codomains, which is the pattern here. Simple arguments, but objects of growing complexity. The same theorem adds two more things. Composition distributes over addition on both sides, and composition commutes with multiplication by scalars. A last corollary. Composing with a fixed t on the right is itself a linear transformation from one space to another. And if t is an isomorphism, then so is that transformation, since composing with the inverse of t undoes it.